All right, guys, welcome. So, what we will do today is I have one question regarding this chemical propellants, and uh, so if you remember last week, we did a problem where we stopped in the middle, like we didn't find the temperature, adiabatic flame temperature, and also we didn't find the characteristic velocity. So if time permits, we'll try to complete it. Since today we are anyway going to talk about adiabatic flame temperature and C star, um, if time permits, we will solve this also. If not, I will leave it up to you to solve. So I took a new question so that we can start from first and then get an idea of how to calculate these things and how are these quantities important. So these things we can discuss today. So before I begin, if you have any quick questions, if you want to ask me, I am open for that. Do anyone have any questions? I think we have around like 3 students here. Maybe more will join sooner.
Hello,
Hello,
I'm
I'm
Shantanu.
Shantanu.
I have
I
a
have a
question
question
from
from
the
the
recent
recent
week,
week,
lecture
lecture
number
number
16.
16.
Okay.
In
In
that,
that,
one
one
of
of
the
the
slides
slides
or
of
one
one
of the
of the
discussion,
discussion,
Professor
Professor
plots
plots
Q
Q
versus
versus
mixture
mixture
ratio,
ratio,
Okay.
and
and
then
then
says
says
to
to
transform
transform
from
from
Q
Q
to
to
temperature,
temperature,
we
we
have
have
to
to
divide by
divide by
Cp,
Cp,
but
but
it will
it will
be
be
complicated.
complicated.
So
So
what it
what it
does
does
is he
is he
says,
says,
let's
let's
do
do
Q
Q
by
by
number
number
of
of
moves
Mm-hmm.
versus
versus.
mixture ratio. In
In
doing
doing
so,
so,
he
he
kind
kind
of
of
uh,
uh,
intuitively
intuitively
Mm-hmm.
plots
plots
how
how
mixture
mixture
ratio
ratio
varies.
varies.
If
If
mixture
mixture
ratio
ratio
uh,
uh,
goes
goes
above
above
stoichiometric,
stoichiometric,
then
then
he
he
says
says
that
that
the
the
because the
because the
number
number
of
of
moles
moles
will
will
increase
increase
for
for
the
the
oxidizer,
oxidizer,
the
the
mixture
mixture
ratio
ratio
Q
Q
would
would
be
be
constant.
constant.
That
That
is
is
the
the
Q
Q
at the
at the
stoichiometric
stoichiometric
ratio,
ratio,
but
but
he
he
then
then
reduces it.
reduces it.
My
My
question
question
was,
was,
instead
instead
of
of
doing
doing
intuitively,
intuitively,
can't we
can't we
do
do
it
it
numerically,
numerically?
as
As
in
in,
the
the
Q
Q
is
is
minus
minus
of
of
heat
heat
of
of
products
products
minus
minus
heat
heat
of
of
reactions.
reactions.
Mm-hmm.
In that,
That
if we
if we
just
just
divide by
divide by
n,
n,
Mm-hmm.
then
then
won't
won't
that be
that be
the
the
accurate
accurate
answer? I
answer? I
mean,
mean,
uh, how to
how to
calculate
calculate
how to
how to
calculate
calculate
it
it?
basically.
So basically, if you take any fuel or oxidizer, so let's say if I try to write this down. So the mixture ratio is nothing but mass of oxidizer by mass of fuel, right? So
Yes.
Yes.
mass of oxidizer by mass of fuel. So you can calculate. So let's say for stoichiometry. So I'm giving an example. So what is the spelling of this? Stoichiometry. So yeah, whatever be the spelling. So let's say the mixture ratio is something like 1. Stoichiometric mixture ratio is 1. For example, this is for an example. Some
Okay.
fuel and oxidizer is present. Okay, fuel and oxidizer gives products. Okay, so if you see in the during stoichiometry, what happens? The stoichiometry. What does stoichiometry means? So let's say if I have a mixture ratio here and Q here, heat of reaction. Is that what you're referring,
Exactly.
Shantanu?
Exactly.
Okay. So let's say this is the stoichiometry. Let's say this is one, or let's say this is the stoichiometry. Okay. During stoichiometry, what happens is uh, the fuel is completely oxidized. Okay, and everything forms the product. So when you have fuel and oxidizer, so once you combust the mixture, what happens is you will have only products, right? So that is what the stoichiometry means, right? So let's say you have some heat of reaction for that. Now
Yes.
Yes.
my question is, now let's say I have 1 kg of fuel and 1 kg of oxidizer is the stoichiometry. This is the stoichiometry. Okay. This is the stoichiometry for this fuel and oxidizer. Now if you do this, then you will get 2 kgs of product. Okay. Now this is giving you some heat release, let's say QS. Now let's say if I increase the fuel quantity, let's say if I have 2 kgs of fuel, okay, and 1 kg of oxidizer. Now what will I get if I combust
3
this?
kg of products, but same quantity of heat.
Exactly. So you will get 2 kg of
Sorry,
products.
sorry. Oh no, this is fuel rich.
This is fuel rich.
Fuel rich. Then Q will be less.
So basically the 2 kg of products you will get, but in addition what you have is the 1 kg of fuel still remains.
1 kg of fuel remains. Yes.
Now what you did was, while you were converting the whole fuel to oxidizer, you formed 2 kg of products, and during that process, let's say there is amount of heat release which is equal to Qs, but
Okay.
the 1 kg of fuel was still remaining, right? So that 1
Yes.
kg of fuel, initially it was at initial temperature, and what you did is you spent some energy to heat that fuel, with so it's a useless waste of heat. So you spend some energy to heat that fuel to a high temperature, right? So
Yes.
that is the reason your Q out is actually less. Q combustion is actually less. Q of reaction
Less.
is actually less,
Okay.
right? So that was one of the reason why you will always have. So if, let's say, if this is the stoichiometry, you are going to have, if it's a fuel rich would be um, this side, right?
Right.
So fuel rich would be always having lesser Q heat release. Okay. Now let's say if you go the other side, so you can actually calculate. You can actually take a fuel oxidizer, and then you can do this calculation. But you actually no need to do that because it is straightforward. That's why professor was meaning to say that you can intuitively say that this is how it is going to happen. Okay, so if you go to
Yeah,
the
my
other,
question.
yes,
Yeah.
yes.
How do we convert this plot to Q per mole? This is Q versus mixing ratio.
Mm-hmm.
How can we convert it to Q per mole to mixing ratio? Because from there we can go on to calculate temperature of combustion.
So it is the same thing. Like, so let's say this is Qs divided by mass of fuel, right? So when you do that, so when would this, let's say this is Q dash, Qs divided by mass of fuel or Qs divided by number of moles of fuel. Okay, both are just a proportionality constant difference, right? So if you multiply by molecular weight or divide by molecular weight, you will get Q per mole of fuel. So so basically, if you're able to find the trend of this one, you can actually easily extrapolate it to Q by number of moles of fuel. Now the question is, what happened was your QS also reduces. In addition, the mass of fuel, as you go to fuel rich, mass of fuel increases, right? Because you initially have a lot of fuel. So that was the reason again, which is going to have a lesser QS. So you can even plot, let's say, QS by mass of fuel in the same plot. Then what you can have is you might have something like this, because Q is also decreasing and the amount of fuel you used is actually increasing, right? So that was the reason you will have you know uh, uh, reduction. So uh, even if you calculate, you are going to end up with the same thing. So it's just the argument of uh, division, which one is increasing. uh, is that what you are asking, Shantanu?
Yes, yes. And the other case that you were just about to discuss was, I think, oxidizer rich case.
Oxidize. So basically fuel lean, right?
Fuel
So
lean.
there what happens? Again the same thing. So your QoS is going to decrease. So basically this is how it will be, right?
No, the Q will remain same because because that's the just the additional mixing ratio will increase, but the Q will remain the same.
Why
But
is
the
it so?
Q plus M will decrease. The trend that you showed now is, I think, for Q per mass of
Fuel.
reactants.
So you mean to say something like this?
Yes, but the blue curve will be flat.
Why do you say so? Blue curve would be flat.
That's because the excess oxygen will not react, will remain as it is. Because anyway, the Q, how the Q is calculated? Q is calculated from heat of formation of products minus reactants and negative sign to it. And because the formation of the oxygen will remain as it is on the product side as well, and because the formation of oxygen has zero value, therefore Q will not change.
Okay, so if it is a oxygen, then it is fine.
Okay. Yeah.
But what if it is some other, let's say like a water? Water can also be used as an oxidizer. So
Okay.
you are right, actually. So it can either be, so it is not always true that it will be flat. It's because of the special case of oxygen, because
Okay.
oxygen has a no zero formation enthalpy. But ideally, if you have some other, you know, let's say some other oxidizer, for example, water is also an oxidizer. Water is not just a product, it can also
Yes.
be acted as oxidizer. Example, H2O2, hydrogen peroxide is also an oxidizer. So if you use these oxidizers, these things have formation enthalpies. So when you calculate it upon increasing oxidizer, again the Q actually starts decreasing.
Okay.
Okay, so yeah, basically it comes from that argument.
Okay. Okay. So the axis for yellow curve is QS by M fuel, or should it be QS per mass of reactants, fuel plus oxidizer?
Um, I'm not sure what was Professor referring to. QS by
I think he
uh,
was referring to mass of propellant, fuel plus
mass.
oxidizer both.
Okay, it's mass of propellant. So let's say if you want to draw that also, you can still draw mass of propellant, which is mass of fuel plus oxidizer. So, um, so in any way, the mass of propellant is going to increase whether you go to fuel rich or fuel lean, right?
Hmm.
So again, you will get the same kind of curve.
Yeah, curve will look similar. Yes.
Yeah. So again, you might get same kind of curve. Whether it will be in between or outside, it depends upon the values, probably.
So
Okay.
basically, the conclusion or the point is Q is maximum only at this stoichiometric,
Exactly.
no
Yep.
simulation. Okay.
That is always true. Q is maximum. The same actually goes with temperature also.
Oh, yes, yes. Okay. Thank you.
Okay. All right. So if there are no other questions, what we will do is we'll quickly solve this question. So here I have a problem where we take a nitramine propellant which consists of 85% of HMX. HMX is nothing but an explosive. It's actually used as a explosive, bombs basically. But what you can also do is you can use it as a propellant. Basically, the combustion is nothing but the propulsion, the combustion happening inside a combustion chamber is actually explosion, but it is controlled. So we can use explosives, but you are trying to control it in order to get certain desired quantities. Okay, so that's why you can also use HMX. It's called some Her Majesty explosive. I don't exactly know the chemical formula, but anyway, so this HMX is actually the fuel, and you have HTPB binder. It's hydroxyl terminated polybutadiene binder. Okay, and the chemical formulas are given, and its heat of formation is also given. The chemical formula for HTPB is this. The heat of formation of binder is this. So that those are also given. So what they are asking us to find is, we are asking us to find the mixture ratio, the stoichiometric mixture ratio. Okay, so this mixture ratio is whatever the propellant quantity. So they have given that 85% of HMX is there, and HTPB binder is there. So for this, what is the mixture ratio is what they are asking. And yeah, let's say if you want to do stoichiometric combustion, then what is the stoichiometric mixture ratio? And third one is moles of product species per mole of HMX, the heat released per mole of HMX, temperature and characteristic velocity. So basically heat release is what we already discussed in the last class, but we'll try to solve again here. So let's see. Um, what do you have is you have HMX. Let's say let me write the reaction. So HMX is C4H8N4NO4. C4H8N4NO2 4 plus added to HTPB binder, which is C200 H302 and O2. And then they didn't give any products. So, and what they also told is it's like 85% of HMX is added to HTPB binder. So this binder is nothing but, so HMX would be like a particles, or uh, yeah, basically it will be kind of like a particles, and binder is nothing but a polymer which binds all this. And in this case what happens, the HMX also comes with some oxygen, which means these can also be used as a monopropellant. In fact, explosives, what you actually do is you do not need oxygen from the atmosphere. The explosive itself has the oxygen. So basically they break down, the HMX will break down into first they dissociate and then into fuel and oxidizer, and then they react, and then they produce the combustion products. But in this case, in addition to this, we also have the what do you have, binder, and binder also provides the oxygen, so this can also act as a oxidizer. Okay, so they are telling we have 85% of the uh, HMX is reacting, is what they are telling. So what does it mean? So they actually didn't say that whether it is a volume basis or mass basis. So maybe we can take in terms of mass basis. So HMX is like 85% of the mass, and HTPB is like remaining 15% of the mass. Okay, so uh, so basically even if you know that, so how would you fill the coefficients here and here? So here it's like you're trying to get number of moles of HMX and number of moles of HTPB. So what they have given is, let me write it down mathematically. The mass of HMX is 85%, right? So basically mass of HMX by mass of HMX plus mass of HTPB is like 0.85. So this is what they have given. So using this we may need to arrive at what is the moles of HMX and moles of HTPB. Give me a minute, 1 second.
Okay, you have PMF, sir?
Yes, yes.
We are giving you keys for this Almira. You can keep your important stuff there because we don't have keys for this.
Okay.
Because two people are there, no? We have one key only.
Okay.
You can keep your important stuff there. There are Almiras.
Okay.
I'll give you one Almira's key.
Okay, sure. When will you be giving it?
Just now, if I'm giving those.
So you can just keep it here. I'm actually in a lecture. Sorry guys. So were you guys able to get what would be the mass number of moles of HMX and HTPB? So
No idea.
okay, no problem. So
You can
basically,
you
mm-hmm.
can divide by molar mass, respective molar masses. You can get the number of moles.
Yeah,
But one
yeah, but we don't really know the total mass, right? So we may need to assume something, right? So we can assume that there is the propellant is total mass of the propellant is 1 kg basically, or mass of HMX plus mass of HTPB is 1 kg. Basically, either you can assume this, okay, or you can take the number of moles of HMX to be 1. Let's say if you take number of moles of HMX to be 1, then you can find the number of moles of HTPB. Okay, so basically what they did was they gave the composition percentage in terms of percentage. So we don't really know what is the total amount of HMX or what is the total amount of propellant present in. Okay, so only they gave only the fraction. With fraction we cannot arrive at the you know exact number of moles. So we may need to assume like per mole basis or per mass basis we may need to arrive at something. So here you can either, so it doesn't matter in which uh, which way you are trying to normalize this. You can either normalize with this way or you can normalize this with this way, but in either way you are going to get the same whatever the quantities they were asking. In either way the mixture ratio will be same, temperature, heat release, all those things will be same, because everything is asked for per mole of HMX, per mole of HTBB. So they were they were asking it like this. So um, since a lot of questions is talking about per mole of HMX, it's actually makes sense to use, it's easier to use number of moles of HMX to be 1. So let's say if you consider number of moles of HMX to be 1, then you can, as Shantanu said, you can just put it here, and you can get the number of moles of HTPB. Okay, so let me do that here. So number of moles of HMX into molecular weight of HMX divided by moles of HMX plus molecular weight of HMX, sorry, plus number of moles of HTPB into molecular weight of HTPB. So this is 0.85. This is what. So this has to be maintained. Okay. So now we may need to find what is the molecular weight of HMX, and how much would that be. So what do we have? C4H8N4. So 4 into 12, 8 into 1, 4 into, I think it's what is N? N is 14, is it? And 4 into 14 plus 2 into 16. Okay, I hope this is fine. So how much is that coming? I missed my lap. I don't have a calculator here. Let's see.
Sir, can you show the formula again?
Okay.
Sir, I think in the equation, sorry, in the calculation you wrote in the brackets, it has to be 8 into 16 because it's
Oh,
4
oh yeah,
times
sorry, sorry.
N14 for 2 7 outside.
Sorry. 8 into 6. Or basically, yeah, I confused it. Maybe you can write it like 2 and then outside you can put 4.
I got 266.
266.
Yeah.
Uh, 4 into 16. I am getting something like a 296.
Yes, the same here. Even I'm getting 296.
Okay. So could you please check once again whether it is 266 or 296? So it's a 14, 2 into 16 is 32. 32 plus 14, 46 into 4 plus 4 into 14.
Yeah, 296. I think I missed
Yes.
some.
Okay, no problem. So yeah, 296. Similarly, what would be the molecular weight of HTPB? So it is something like 200 into 12 plus 302 into 1 plus 2 into 16.
Two seven three four, 2734.
Okay, 2734. So basically, the reason for this to be very high is actually HTPB is a polymer, and they were truncating this at some point. So that's why you have C200H302. That is the reason you have 2734 grams per mole. Anyway, so let's say if you substitute these things over here, HMX is 1 into 296 by 296 plus NHTPB into 2734 equal to 0.85. So how much is the number of moles of HTPB is coming out to be? So it's 296 by 0.85 minus 296 divided by 2734. So I'm getting something like 0.0191. Are you guys also getting this?
Yes.
Okay, thank you. So this is done. So maybe we can find the mixture ratio now. So what would be the mixture ratio? So mass of oxidizer by mass of fuel. So that is going to be equal to. So oxidizer here is, we are now going to consider HTPB as our oxidizer. So if that is the case, what would be? So N of HTPB plus molecular weight of HTPB divided by N of HMX into molecular weight of HMX. So 0.0191 into molecular weight of HTPB is 2734 divided by HMX is 296 into molecular N of HMX is 1.
Point 1764.
Okay, wonderful. 0.1764. So this is the mixture ratio. So your mixture ratio is nothing but 0.1764. Now we need to find whether it is a what is stoichiometric mixture ratio. Stoichiometric. So how do you find the stoichiometric mixture ratio? Anyone have any idea?
By
By
completing the
completing the
reaction,
reaction,
calculating
calculating
products.
products.
Right. So what are the products you will consider?
Carbon dioxide, water, and I
I
guess
guess
nitrogen.
nitrogen.
Okay. Why is that? Why is that only carbon dioxide, hydrogen? So actually, whatever
So
you
in
said is
between
right.
it's complete combustions
Combustions
of
of
all
all
possible
possible.
we are
Yeah.
considering.
Right. So actually, whatever you said is right. So stoichiometric means upon complete combustion, you will have ideal set of products. So the products is ideal. So that is important. Okay. Which means there won't be any remaining fuel left. There won't be any remaining oxidizer left, and you will be having ideal set of products. Okay, so let's say if you have a hydrocarbon and the oxidizer, then you are going to have CO2, H2O, and N2. So every element, every carbon will be oxidized. Every hydrogen will be oxidized. So if you want to get an ideal set of products without any fuel and oxidizer, then that is how you will get the stoichiometric reaction. Once you get the stoichiometric reaction, you can find the stoichiometric mixture ratio. Okay, so let me check whether my recordings are going on. Okay. So,
Excuse me,
Excuse me,
why
why
not
not
NO2?
NO2?
so um, good question. Why not, do well? You are not uh, interested in oxidizing nitrogen, right? So let me think. Actually, yeah, actually you are right. So we have nitrogen. Why not? We should have NO2.
Because generally
Generally,
in
in
gas
gas
turbine
turbine
propulsion, we
propulsion, we
see
see
NOx
NOx
and
and
SOx
SOx
forming,
forming,
NOx, SOX
SOX
forming. That's
Mm-hmm.
often
often
in
in
the
the
discussion.
discussion.
Mm-hmm. So
So
actually, it is not ideal.
as far
Far
as
as
I
I
know,
know,
the
the
reason
reason
is
is
because
because
NO2
NO2
and
and
NO
NO
both
both
have
have
positive
positive
heats of
heats of
formation
formation
at
at
25
25
degrees
degrees
centigrade.
centigrade.
Okay.
So
So
we
we
will
will
take
take
25
25
degrees
degrees
centigrade
centigrade
and
and
1
1
atmosphere.
atmosphere.
So
So
there it
then it
will be
will be
having
having
positive heat
positive
of
heat of
formation,
formation,
therefore the
therefore the
molecule
molecule
is
is
unstable.
unstable.
But
But
maybe
maybe
there
there
might be
might
something else
Uh,
against
it,
that.
that.
it could be, but actually, what we are interested. So this stoichiometry is like what we are interested in. So when you have a complete combustion, what you want to have is you want all the fuel to be oxidized. So which means nitrogen is actually not in your fuel. Nitrogen doesn't come as a fuel. Okay, so uh, NO, as Akhileshwar said, basically NO2 will be having NO2 will be classified as a fuel because it will not have zero heats of formation. Okay, so all these, one second. So all these products actually, so N2 has a zero heats of formation, and these products will have minimum heats of formation, for example. So because the heat of formation here would be very high, and the heat of formation here would be very low. So if you have NO2, then the heat of formation would be high there, which means like you are uh, it's not so it actually classified as a fuel. So that is the thing. So here it is like fuel is getting oxidized. So if you consider oxidizer as your fuel, which means uh, oxidizer is kind of losing oxygen, and the fuel is gaining the oxygen, right? So you would expect uh, only this to happen, because this will have the least amount of hits of formation, and that is the maximum amount of energy you can get out. So if you form NOx, then you have spent some energy on it. Okay, and that is
Yes,
one of
exactly. Exactly.
that is one of the
Because it will absorb some heat for itself
correct,
to form
and
this.
that will not be an ideal set of products then. Exactly. So if you form the NOx, let's say for example in gas turbines they see NOx emissions, so they try to reduce the NOx emissions. They do not want this NOx to be emitted. Okay, so that's why we are not interested in forming NO2, and also it is like it's not the ideal set of products. But your question is valid.
Okay.
Let me give a little more thought in it, then I will get back to you. Okay. So at the end of this stoichiometric, we are actually oxidizing all the elements. Why not N also to be oxidized? So whatever Akhilesh was said is correct, uh, but I will come up with a better explanation maybe in the next class. Okay. All right. So now we just need to balance the reaction. Let's balance the reaction. Um, so let's say we'll take 1 mole of HMX. Okay, and we are trying to find this number of moles of HTPB. That is one of the aim. So if that is the case, what would be the these quantities? So we can easily do N2. So this is going to be 2, right? 2 N2, 1 mole of HMX. And how about, let's say if you do carbon atom balance, you will have 4 plus 200 N HTPB of stoichiometric is equal to some A and B, let's say A. Okay, and let's say if you do oxygen atom balance, how much would that be? 8 plus 2 times N more N of HTPBS equal to 2A plus B. And let's do hydrogen atom balance. If you do that, 8 plus 302 of NHTPB, yes, is equal to 2B, right? Did I write it right? So now you have 3 equations, 3 unknowns. You can directly get A, B and N, right? So can anyone calculate and let me know? So let's say if I go ahead and do some smaller calculations. Two into 4 is 8 plus 400 N HTPB, yes, plus B. 8 gets cancelled, and then you have B is equal to something doesn't feel right. Anyway,
It's coming up with negative one.
-1. You sure?
Yeah. Okay. I don't know. I was getting it. I'll check.
Okay.
Number of moles of HTPB are known. 0.0191. calculated above?
See that 191 is based on the 85% of mass, right? We don't know whether this 85% of HMX is actually and 15% of HTPB is actually the stoichiometry.
Okay, so we
We
want the
don't really know
stoichiometry.
that. Yeah,
Okay, okay.
that may or may not be stoichiometry. Hmm. See, actually, this equation actually gives like minus 398 of n times HTPB. Yes, which means something is actually wrong in the reaction. Can you oxidize this properly? Hmm, did I write the equations properly? Okay, n is, wait a minute. So this is C. So n atom balance. You will have 8. 4 plus 4 is 8 here. Is equal to 2C. So this will give you C is equal to 4. So n is balancing, which means actually you do not have enough oxygen to balance both to balance and get carbon dioxide and water vapor. If
We
you
need additional
uh,
O2
we need
from air.
additional you were still not able to get positive B, right, or positive N of HTBB. Mm, so for oxygen atom balance is 2 times 4 is 8 and 2 times NH2PB is equal to 2A plus B, and for carbon is 4 times 200 HTBB. So you have like 200 carbon atoms, so at least you need like 400 oxygen atoms to get carbon dioxide fully. So basically what I'm trying to say is you actually should have additionally oxygen in order to get the proper stoichiometric ratio of this to get the stoichiometric mixture ratio. So it's not really coming out to find out stoichiometric mixture ratio. You guys understood what I'm trying to say? Mm, looks like no. So let's say I have some additional X of O2. Okay. So now if I try to do, then what I will have is I will have additionally 2x here. Okay. Now I need to give the number of moles of HTPB in order to find out what would be the correct amount of oxidized oxygen you require. Okay,
Yes, sir.
right? So basically you now end up with like four unknowns and three equations, maybe three equations. So that is one of the problem with this kind of propellants. So they have the oxygen within themselves. So ideally you cannot reach the stoichiometric mixture ratio, or ideally you cannot get the ideal set of products. So that is not possible at all with this kind of propellants. So you see, you have HMX which has oxygen in it, you have HTPB which has oxygen in it, and the carbon atoms and hydrogen atoms present here has to fully depend on this oxygen only, right? And until unless you have some additional oxygen, you won't be able to get ideal set of products basically. So
But
even
is
if
there any question asking for stoichiometric ratio between this HMX and binder?
so
Maybe if, but okay,
yeah, so
stoichiometric mixture
can you
ratio.
can you continue, what were you
Yeah,
telling?
so they have given this composition of 85% of HMX with binder.
Okay.
If we continue with the same propellant, if we have HMX plus with that much percentage is one kind of propellant, and we solve for X, then we left with three unknowns and three equations, where N becomes NHTPB,
Right, right.
and then the X, then we can balance the reaction and
Reaction.
calculate the.
Exactly. So basically, let's say if you take this to be 0.191, okay. So I think the iPad is stuck. So are you guys able to see my screen? Is it stuck?
No, sir, it is completely visible.
Okay. I think for me it is stuck. Anyway, so I just wrote to 0.91 here. I'm highlighting it. Are you able to see? Okay. Okay. So basically, let's say if you take, as Shantanu sir, if you take this as 0.0191, and then you can find what is the amount of oxidizer, and then you will be able to find what is the mixture ratio with respect to the amount of oxidizer you need. But I think this is actually the additional question I wrote. So there's a possibility that this might be this doesn't make sense for this question. Okay. So
The reason I'm saying so is because if we change in NHTPB to NHTPBS, then the composition changes, right? The mixture ratio 0.85, which is given, will change.
correct, yeah, true.
So essentially, the propellant is different. We are dealing with a different propellant than when we started.
That is also true. Yeah. 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 Okay. Anyway, but at this point of time, we can just ignore this question. Okay. Stoichiometric mixture ratio. So, but
So
again,
we can have without means we can remove the X and take an HTTPS 0.0191 and then we can try it once.
okay, if you want to try it, okay, let's see. Then what would happen?
So 2X can be removed, means no extra oxygen we are needing.
Okay.
And
So if you put 0.191, then that is a mixture ratio which we already found out, right? 0.1764.
so it will be exactly same.
Uh-huh. So that's what. So this is a mixture ratio we already found out, assuming that only HMX and HTPB is present without any additional oxygen. So if you don't add this, then this two would be almost it will be same only, right?
Okay, then means the propellant cannot be combusted under stoichiometric conditions by itself.
Exactly. That's what
Okay,
it
we
means.
need that fuel rich or fuel rich thing has to be.
So here it's basically either in fuel rich or fuel lean side. It depends upon which you are
But
calling
fuel
it
rich
as a
only
fuel.
we need because we are lacking oxygen at the end. Na? As we
Uh-huh,
found, we
no.
were lacking oxygen. So
Exactly.
maybe it must be fuel rich.
Hmm.
So the propellant is specifically designed for fuel rich combustion only.
Correct.
Maybe.
When you fix the 85% thing, it's actually fuel rich combustion, and you cannot get the stoichiometry out of it. Yeah, you are right. So oxidizer is less. So yeah, I feel that this question is irrelevant at this point of time. So basically, I thought since mixture ratio has been asked in the question, so I thought I will show this to you, but it's irrelevant anyway. Leave this thing. Let's go forward and solve for moles of product species per mole of HMX. Now it's a interesting thing. Let's see. So they are asking us to find number of moles of product species. So how do we find out? So what is the products? What are the products we are looking at? So since we found out that the oxygen is not enough, so some fuel is going to remain as such. Okay, and so then what are the products we expect?
So then, if we can ignore that dissociation thing, then CO and CO2, H2O,
And
even maybe nitrogen we will also be able to form.
okay, let's assume that nitrogen forms because we are already starving of oxygen. So let's not give some oxygen to nitrogen. So so in ideal scenario, let me emphasize that. So in ideal scenario, nothing of these things will happen. Okay, in ideal scenario, I will tell you what happens. You will have a product composition. You will have CO, you have CO2. I guess I discussed this in the last class also. You will have H2, you will have H, you will have O, you will have O2, you will have H2O, you will have O3, ozone also could form, and
OH even share.
OH, yeah, it's actually important radical. OH, N2, NO, NO2, okay, and NH3. All this is also could form NH3.
Yeah, yeah, yes, sir.
So similarly, like that, I can have 100 species, and all these things could form in reality. In reality, whatever we calculate today or in your exams, it's not going to be there in the reality at all. So in reality, that's why they try to find what is the NOx emissions. NOx emissions is nothing but NO and NO2. Okay, and if you have sulfur, you will have this SOx emission also. So here we have only NO2. So in reality, all these things could happen, and solving this requires a sophisticated approach that we were discussing yesterday, sorry, I mean last week, right? So what we will do here is the few arguments we are going to take. Last week we had the argument in the question itself. Here we are going to assume certain arguments. The arguments are simple. Basically we will tell, uh, let me remove this. So basically we will tell, first hydrogen gets oxidized. All the hydrogen present gets oxidized. Okay. So all the H present will become actually H2O. First this gets oxidized, and next carbon gets oxidized to carbon monoxide. Carbon oxidized to carbon monoxide. And if there is any oxygen left, then carbon monoxide forms the carbon dioxide, and assume that nitrogen just forms. Okay, this is kind of like a simplified chemistry you are going to use in order to come up with the number of moles, product moles. So this is also will be given in the questions. If you look at your assignments, these arguments would be given in the question, telling that consider hydrogen forming first, carbon forming first. But actually in reality also this is sort of this is how it happens. Most of the hydrogen gets oxidized because hydrogen is more reactive, and carbon dioxide also, carbon also gets, first it gets oxidized to carbon monoxide only, and then only it gets oxidized to carbon dioxide. So in reality also sort of you can approximate like this is what happens. But what is also the problem is the temperatures are very high. Whatever H2O you form can actually dissociate and form H and OH. Okay, can actually dissociate and
Yes, sir.
H and OH. These dissociation reactions could happen because the temperature is very high. So that will make the problem more complicated. So for now, let's assume that these dissociations doesn't happen, and this is how it reacts. Okay, so if this is the way it reacts, we know the number of moles of H2, HMX and HTPB, 1 and 0.0191. So now we can actually find the moles, right? First, let's say we'll oxidize all the hydrogen. What would happen here? So you have 302 hydrogen, 302 into 0.0191 hydrogen. So if you divide it by 2, you will be getting something like 2.8841. Okay, so I'm basically doing first the first I am taking 302 into 0.0191 H, and what I am doing is I am adding O2 to it, okay, to get 2.8841 H2O. Okay, so how much amount of O2 I might need? So 2.8841 divided by 2 O2 I need. Okay, let me add as oxygen for the sake. So because of this, so what is the amount of oxygen present? Initially oxygen was present like 8 oxygen was present in the HMX, and 2 into 0.0191 oxygen present. So 0.0191 into 2 plus 8. So we have like 8.0382 oxygen atoms present, and in that we used 2.841 oxygen for the 2.8841 oxygen for the H2O formation. So the remaining oxygen left would be how much? 2.8841. It will be something like 5.1541. Okay, so then what happens is 5.1541 oxygen is available, 5.14 oxygen is available for CO and CO2. Okay, for the formation of CO, Now depends upon the number of carbon atoms we have, we will have that formation. Okay, so how many carbon atoms we have? We have like 4 carbon atoms here, 4 carbon atoms in HMX, and 200 into 0.0191, 200 into 0.091. So you have 3 plus 4, 7.82 carbon. So these many carbon atoms are present. Okay, so but I have only 5.1541 CO, which means I don't even have enough oxygen to form CO itself. So so maximum CO I can form is only this 5.1541 is the maximum CO I can form. So let's put that also here. This is the maximum 5.1541. 1541 is the maximum CO I can form, and uh, N2 I can simply write this is going to be 4N2, right? So 4 plus 4 8, here also 8, which means I cannot form any CO2, okay, but I will be left with some carbon atoms. That is what it means, right? 7.82, let's say 5.1541 is nothing but 2.6659 carbon atoms, just C. See, it just remains as a C because all the other things has formed into CO, and the remaining thing is just remains as a C. But in reality, how can you just have a carbon atom, right? You can simply not have the carbon atom, but we cannot.
So it will form as a suit,
True.
the blackening.
It is true, but soot cannot have simply carbon. That's what I'm trying to say. So it will not be simply carbon. So actually soot can also have CH3 and all kinds of hydrocarbons. Basically, you can have CH.
It's a paraffin that can form. The
The
paraffin.
So all kinds of this can be formed. Here what we have is, since we cannot solve the complicated phenomena, we are trying to simplify it, and we are trying to get this as our for now we'll assume that carbon remains as a carbon, okay, and all the other things gets oxidized. So this is how you actually find out. As far as your exam is concerned, or as far as your assignment is concerned, you can go forward with this approach. But in ideal scenario, how will you find it? So I'm talking.
So for stoichiometric mixture ratio, can we take 0.15 moles of oxygen and the rest the fuel?
Can you come again? 0.15 moles of oxygen. Oxygen, is it? O2?
So because 85% of HMX is given.
Right. So where is HTPB? You need to consider HTPB also, right? I would say you do not worry about this stoichiometric mixture ratio. The reason is this is something I made it. So it may not be you may not be able to get this at all. Okay. So you no need to worry much about this, at least for this question. So is this what you're trying to say, Tanisha? You have 85% of HMX, and you want to directly oxidize with the 0.15 moles of O2.
Yes, sir.
You're not considering HTPB?
Yes, sir. We should consider it.
So if you consider it, still you are getting 0.15 moles of O2, or you are not considering? Anyway, I mean, don't worry about it. So you may not be able to end up getting stoichiometric mixture ratio. That is evident actually. So we cannot add actually oxygen because it's you cannot have a propellant. So let's say this kind of propellant is actually used in rockets, especially solid rocket motors, and there we don't have additional oxygen supply. So if this is the configuration, then that means it's a fuel rich and you cannot fully oxidize it at all. Okay. And also this also actually makes sense because the uh, it's kind of like a monopropellant which has both fuel and oxidizer in it.
Okay, sir.
Okay. Anyway, coming back to this, let's say if I want to really estimate this, what is the product species, how will I do it? Any idea? You guys have any idea? So this is following these arguments that this is how it happens, but in reality this is not how it happens. Any idea how can we get this?
No.
Okay, so no problem, I will tell you. So basically there is something called chemical equilibrium analysis. Okay, so if you have free time you can just look for it. Chemical equilibrium analysis. Okay, there are few uh, web-based programs, like, so you have like NASA CEA, chemical equilibrium analysis. So what you do is you go there and you put that I will have this much hydrogen, this much oxygen, and combust it and show me what are the product species you will form. It actually considers the dissociation happening because of the high temperature. It considers everything, and then it finally gives you what are the product species composition. Let's say if you combust that, what is the equilibrium products you are going to get for a real system. So it is still a theoretical calculation, but it is more accurate than what we do in hand calculation. Okay, so if I get time, maybe to next week, I will show you the NASA CEA. So if you are interested, so what? But this is something you can explore it. You can just Google, type in Google like NASA CEA, and the program will open, and there you just give the let's say hydrogen and oxygen. This is how these are the two things which reacts, and then it's actually self-explanatory. If you go there you will understand, and then it will combust it. It will show you temperature, C star, ISP, everything it will show you basically. um, so I highly recommend you guys to go and visit this. So basically this is based on so in it is actually includes this Gibbs free energy minimization, which is basically you are using second law to find out what is the most possible state. Okay, because second law will tell that, so any physical process should uh, when I say second law, it's second law of thermodynamics. So any physical process should obey these laws. Okay, first law and second law of thermodynamics. The first law of thermodynamics is what is going to give you the temperature, and the second law of thermodynamics is will tell you what is the expected state of product mixture which will have a highest entropy, because we are the nature always tends to maximize the entropy, right? So it will give you the mixture composition which has highest entropy, or in other words which has minimal Gibbs free energy. Basically it's come from thermodynamics. So from there you will be able to get product composition, and that is how they call it chemical equilibrium analysis. And they also solve the first law of thermodynamics to get the temperature also. Okay, so this you can do it. And basically what are they asking in the question? Let's say if you go into the question, they are asking what is the moles of product species per mole of HMX. What is the So basically they are asking what are the number of moles of product species for 1 mole of HMX. So what we did was we actually took this as a 1 mole. So the summation of this would be the number of moles of product species you will get for per mole of HMX. Okay, so that calculation you can do by yourself. So this is done. And now we need to find heat released per mole of HMX. Okay, any questions till now?
No.
Okay. So what is the heat released per mole of HMX is what we are finding. So I have few questions. You have enthalpy, okay? You have total enthalpy. Upon combustion, will the enthalpy increase?
It will decrease means the heat will be released into the environment
Okay.
of the system.
Okay. So
The system will release heat in combustion. I guess.
okay. Okay. So let me restate it. Will total enthalpy increase?
But means total enthalpy means we are saying of the universe, like both the system and its surrounding.
No, no. So that is not total enthalpy. So when you say total enthalpy, it is nothing but total enthalpy of any species or any gases. It's nothing but formation enthalpy plus sensible enthalpy. This is how you define it actually. So will this total enthalpy increase or decrease during combustion? Or what will happen to total enthalpy during combustion? Silence.
It may remain same means.
Remains same. So any other answer?
So when we say sensible enthalpy, means the enthalpy associated with the temperature, right?
Right. So we have one answer remains same. Any other answer?
In my opinion,
Must increase. I think my answer is it should increase as a result of the chemical reaction.
Okay, we have increase. Any other answer? As a result of chemical reaction, you are telling enthalpy will increase.
Yeah, that's how we have the total heat of formation of the products minus the heat of formation of the reactants gives us the combustion, heat of combustion. And that is what is the difference, the increase. Of
Okay.
course, giving it to saying because it is deficit
Okay.
given to the atmosphere.
Okay.
Now there is a rise in temperature. Rise in temperature indicates that enthalpy increases as well.
Okay. I will soon come back to
So
that.
long as it is external reaction.
Okay. Any other answers anyone else have? We have remains.
Enthalpy remains constant.
Okay, remains constant. We have two answer. One for increase. One. Is there anyone who says decrease? All right. So, okay. So it's actually a tricky question. You wanted to so it's about when we say total enthalpy. So that's why I rephrased the questions. It's actually total enthalpy. So when we say enthalpy, it's actually the energy content in the mixture, right? It's the energy of the fuel and oxidizer. So now when it is in, so uh, during the combustion, what happens is, whatever the chemical energy stored, okay, chemical energy stored in the form of formation enthalpy, it gets converted to sensible enthalpy. Sensible enthalpy is something we can feel. It is associated with the temperature rise. So if the temperature rises, which means you can feel that enthalpy also increases. So that is sensible part of the enthalpy. Okay. So basically you are converting the formation enthalpy to the sensible enthalpy during the combustion. Okay. So ideally, if you see the enthalpy of the mixture, enthalpy of the propellant mixture, and also enthalpy of the products upon combustion you have, they both will remain same. Only thing is temperature rises. So if the temperature rises, doesn't automatically mean that enthalpy will increase. So for example, let me draw in terms of let's say bar diagram, which would be easier for you to understand. So I have fuel, okay, so this is total enthalpy, okay, and so I have fuel, okay, enthalpy comprises of both formation enthalpy and the sensible enthalpy, okay. So the fuel always have higher formation enthalpy because it should have higher formation enthalpy, then only you will be able to harness those energy as a increase in temperature or as a heat release out, okay. So formation enthalpy is something within the fuel and oxidizer, and you want to extract those enthalpy, you want to convert those energy into something which is useful to us. In our case it's heat, okay. So here your mixture will be at let's say 298 Kelvin. So you have fuel and an oxidizer and it is at 298 Kelvin. So if it is at 298 Kelvin, then what do you actually have is, you have some amount of formation enthalpy and you have some amount of sensible enthalpy. So whatever I draw in blue is actually formation enthalpy, and whatever I draw in blue is nothing but sensible enthalpy, and whatever I draw in red is actually formation enthalpy, okay. So now upon combustion, what happens is, you convert all these formation enthalpies or most of this formation enthalpy into sensible enthalpy. So that is what exactly happens. So this is for reactants, okay, and for products your formation enthalpy will be very low. Those are low energy products, and your sensible enthalpy will remain high. So remember, enthalpy is nothing but a form of energy. So you can measure energy in terms of enthalpy in this case, right? So what do you have is, this is products. So ideally the total enthalpy of reactants will be equal to enthalpy of products. This is what actually first law of thermodynamics says, okay. But the formation enthalpy has become sensible enthalpy in this case, which we are going to use it to extract it as a heat, okay. So during combustion, what happens is, there won't be any absolute change in enthalpy, okay, total enthalpy. When I talk about enthalpy, it's total enthalpy. And what happens is, the formation enthalpy which was present in the reactants, it's getting converted to a sensible enthalpy when it is in products. So that is why when you try to find out temperature, so this is because then if this is the case, then the product should be at higher temperature, right? Product should be at higher temperature. So that temperature is what we call it as an adiabatic flame temperature. So what do you have is, you have a box which contain reactants, and it's an uh, adiabatic box, okay. And upon combustion, what happens, this box will have products. Here the temperature would be T initial, let's say something like 298 Kelvin, and the temperature here, again as I said, if it will be a box without any heat losses, the temperature will be somewhere like T adiabatic film temperature, okay. This is what happens during combustion, and the temperature you get here is adiabatic flame temperature, because you are adiabatically you are combusting it and trying to see what is the temperature it will reach. That is why it is called adiabatic flame temperature, okay. Now you should ask, then what is this Q release, right? So this Q release is nothing but, once you reach all the products, okay, this products has formed. Now you remove this adiabatic, okay, and you get all the energy you out of it, okay. What happens if you do that? Now you will have products, and then you remove this adiabatic component here. Now the temperature again will get back to T initial, but now it is purely products, it is no more reactants. Then what you actually did is, during this process, what you did was, you took out some Q, and this Q is nothing but the heat of combustion or heat of reaction, okay. Because see, you are starting from initial temperature of 298 Kelvin, but at that time it was fully reactants, there is some energy, and you are combusting it and you made it fully products, but the temperature is high. See, everywhere, so from this process to this process is also energy is conserved, okay. Energy is conserved. From this process to this process is also energy is conserved, and energy should always be conserved. That is what first law of thermodynamics says, okay. So if you follow the first law of thermodynamics, and that is true, energy can neither be created or not destroyed. So whatever the reactants which has formation enthalpy in it, it is get released as a sensible enthalpy, and that's why you will reach a higher temperature. And the Q reaction you get is when you cool down that products to an initial temperature. Only then you will be able to harvest this whole sensible enthalpy part, okay, and that is what will give you Q reaction, okay. And so this will be at, so this is at T initial and this is at T adiabatic, okay. And if you are able to harvest this whole sensible enthalpy, this will be your Q reaction, okay. Were you guys able to understand what I'm trying to say? Do you have any doubts in this?
No, it's clear now.
Okay, thank you. So
Well, I have a doubt. So, I understood the concept of adiabatic temperature. So, essentially, do you mean that if we divide Q by Cp, then will we get adiabatic temperature?
it you can actually say that, but depends upon what CP you divide.
Cp of products, when net Cp.
Right. So if you the Q, so what are you trying to get? So Q divided by Cp of products will give you adiabatic flame temperature. Is that what you are trying to say?
Is that how we can calculate?
So so actually what happens is, let's say if you do a energy conservation from here to here, So how will you do the energy conservation? So from here to here is what actually what you are trying to say is actually you're doing energy conservation. So whatever Q you get heat released is nothing but Cp times T adiabatic minus T initial, right? But this is not always true. Only if you consider Cp is not a function of temperature, okay? But your temperature varies from T initial, it's from 200 Kelvin to like 2000 3000 kelvins, right? During this process Cp will not remain same. Cp will continuously vary, or Cp will continuously increase. So only if you say H sensible is equal to Cpt, then only this is valid. But ideally H sensible is not CPT. So let me tell you what is H sensible. H sensible is nothing but integral of Cp dt from any from T initial to whatever, not T initial, 298 Kelvin, or T initial to whatever the temperature. This is the sensible part of the enthalpy, okay? Because Cp is also a function of temperature. You should know that.
Sir, what is the heat utilized and heat loss?
Heat utilized for
Yeah, you got the sensible heat after combustion. So in that, what is the portion of utilization and what is the portion of the loss? Especially in context of say propelling the rocket.
So there what happens is, while you have the rocket propel, so heat is released from the combustion, okay? So let's say if you have a rocket something like this, the whatever the gas is coming out, it combusts and then heat gets released, okay?
Yes.
So ideally what happens is not heat releases, so the products will form and the products will have higher temperature. So it's not really the heat of reaction we are talking about, it's actually adiabatic flame temperature inside the rocket we are talking about. So the temperature is very high, and if you harvest all this product and then if you convert it into if you cool down the products, then you will get some heat. That is the heat of reaction that we are talking about, the delta Hc or delta H or everything. In addition to it, since the adiabatic flame temperature is very high, there is a possibility in any rocket or let's say gas turbine engines. What happens is outside the temperature is T infinity or T lesser temperature, there is always a tendency for heat to be lost outside. So this is like completely different concept. This is because there is a temperature gradient from
No,
inside.
I'm not talking of only the nozzle loss. I'm talking about we get a exhaust velocity Vj.
Correct.
Okay. So that is the actual useful work. The exhaust velocity or the characteristic velocity.
Right.
And whatever the jet has gone out, so how much percentage of heat is lost? That heat is not 100% utilized, no, sir.
Correct.
So that I should have some concept on that.
Okay, so
Now in the chamber, the products are burned. So it develops BC and VC, that is velocity, and pressure.
right.
Then we will increase the velocity through nozzle by choking it at Mach 1A, that is Mach velocity. And later on again, the pressure is increased above the atmosphere and the combustion products are exhausted.
Correct.
During the exhaust, when it is exhausted, so it creates thirst and the rocket moves up.
Correct.
Right, sir? So how much portion of this heat energy is utilized in propelling the rocket or in giving the momentum to the rocket or the full rocket and the full structure? And how much exactly it is lost? That we should have some concept in that aspect.
Okay, so So it actually from the nozzle.
It is not full 100% heat has been utilized. That I am sure.
Yeah.
So some heat is lost.
Right. So when you say heat is lost, it is actually like a energy lost. Whatever the energy you generated in the combustion cycle,
Exact term is energy loss.
energy is lost. So what you actually do is you will convert this whatever the energy you have in the chamber to the kinetic energy you have here, right?
Okay.
So during this expansion process, you may not be completely expanding all the it comes in the expansion process, how efficient your expansion process is. So this is the delta H you have, okay, and this is actually used for so if you do a if you do a energy conservation from here to here, whatever you have is kind of enthalpy, or basically you can write it this as, so whatever the enthalpy with which in the chamber is nothing but enthalpy at the exit, okay, plus V square by 2, right? This is
So this H2 is the loss.
exactly, this H2 is the loss, but yeah, you can say that this H2 is the loss. So ultimately you want all the H1 to be converted into V squared by 2, but it doesn't happen. Always air comes out with a certain temperature. You cannot cool it down to sub-zero, like 0 Kelvin, right? So only at let's say like 0 Kelvin, then only you will have lowest enthalpy.
Okay. And generally, how much percentage it will be, sir, approximately?
It depends upon the expansion ratio and also the expansion, the efficiency, nozzle efficiency we talk about, right? So it actually basically from ISP and C star you can actually get that. It's actually the propulsion efficiency you are actually talking about.
Okay.
All right. But I hope this concept is clear. What is heat of reaction and what is adiabatic flame temperature? This concept, you should not mix these two concepts together. That is what I wanted to convey. Is everyone clear about this?
Yeah, clear.
Okay, thank you. So now, what we will if you want to find heat release, so let me give you a different perspective of this. It is based on the first law of thermodynamics, as I said, from the first law of thermodynamics. From the first law of thermodynamics, and let's assume this is a constant pressure process. Actually, you can define the adiabatic flame temperature for constant volume process also. So when I say constant pressure process, here I have these boxes, right? So these boxes, so if I have a pressure is equal to 1 atmosphere here, here also I can maintain the pressure at 1 atmosphere by changing one of this thing as a piston. Okay, so I can adjust my volume to make it 1 atmosphere. So it's like a constant pressure process. During this constant pressure process, one thing hasn't changed, the energy content, because it's an adiabatic wall, no energy is going to go out. Okay, and also you have done work because of the motion of piston, but that work is already taken care by enthalpy. So in terms of enthalpy is purely defined for constant pressure process. The enthalpy doesn't change during the combustion. Okay, so using simply that relation, you can arrive at delta Hc, you can arrive at adiabatic flame temperature. So you have what do you have at state 1? This is state 1 and this is state 2. State 1 will have some enthalpy, which is enthalpy of reactants. Okay, and state 2 will have enthalpy, which is enthalpy of products. Okay, and first law of thermodynamics says that enthalpy of reactants is equal to enthalpy of products, and this is sufficient for you to find an adiabatic flame temperature. Only thing is you should know what is enthalpy of reactants and what is enthalpy of products. So how will we define enthalpy of reactants? Enthalpy of reactants can be defined as it's going to be summation of all the species. So whatever the reactant species you have, reactant species in the sense fuel and oxidizer basically. So for I is equal to 1 to some capital N. This is the N number of species you have for the reactants. Ni into Hi, where this H is also total enthalpy. And since it's in total enthalpy, you may need to write it in terms of, let's say, sensible enthalpy, formation enthalpy and sensible enthalpy, which you can write as Hf of I plus integral of Cp of I. So remember, Cp is not constant for all the species. Cp is going to be different, and it is also a function of temperature. And how will you go from how will you find the enthalpy of reactants? So enthalpy of it would be at some initial temperature, right? So if it is at initial temperature, then the sensible enthalpy part is going to be simply from 298 Kelvin to T initial. This is how we define the total enthalpy itself. Okay, and similarly you can define enthalpy of products. Okay, summation of I is equal to 1 to capital M, let's say, into Ni of NiHi, where N is capital N is number of reactants and capital M is number of products. Now if you do that, the same thing, there is nothing difference, just one formula you should remember, and that too it's a first law of thermodynamics. So this also you can write this as Hfi plus integral of Cpi dt, but now the temperature is from 298 to this adiabatic flame temperature. Okay, because we know at the end this is from 1 to 2, right? So from here to here we know it is going, temperature is going from 298 to adiabatic flame temperature. Then the sensible enthalpy, if you want to calculate, it should be from 298 to adiabatic flame temperature. Okay, so this is the only thing you should remember. And now you just equate it, enthalpy of formation of every reactants and products, Cp's of every reactants and products. You can now assume that Cp's of reactants and products are actually constant, and for this case you can assume that it's not a function of temperature, and you can write the equation down and you can directly find the adiabatic flame temperature. So to find the adiabatic flame temperature, you no need to really find enthalpy of reactions. So probably in the lectures you might have noticed that enthalpy of combustion or enthalpy of reaction, delta Hc, we first find it out, and then we will just find what is the sensible enthalpy difference, and then try to find the adiabatic flame temperature. That formula and this formula more or less same. So basically, if you the difference between these two is what is giving you the enthalpy of reaction, and difference between these two minus this is actually the you use it for enthalpy for the adiabatic flame temperature. But this can be simply obtained from telling that enthalpy of reactants equal to enthalpy of products. Now you just put this on the either side and you will be able to solve it. Is this clear? So this is from the basic principles.
Yes.
Okay. So only thing you need to remember is total enthalpy doesn't change. That is the only thing, unless you take heat out of it. Okay. So only when you take heat out of it, your total enthalpy is going to change. Only when you take this heat out of it, your total enthalpy is going to change. So if that is the case, so I guess enthalpy of reactions, Q reaction you can always find, but we also last time we discussed also. So I will leave it up to you, and I will directly go ahead and solve try to find the temperature of product species. Okay. So first we need to find enthalpy of reactants. So which is nothing but number of moles of HMX plus number of moles of HMX into formation enthalpy of HMX. Let me stick with the same notation. Formation enthalpy of HMX plus Cp of HMX from T initial minus 298. So basically I did the integration here itself, okay, and then plus N of HTPB into formation enthalpy of HTPB plus Cp of HTPB into T adiabatic minus 298. Okay, so you know HF, you know Cp, you know T initial. Oh, I'm sorry. Why did I write T? T initial. This is just only this part, right? So we have two species, HMX and HTPB. So that's why both will have. So basically, what I'm trying to calculate is I'm trying to calculate this enthalpy, and then I will equate it to this enthalpy. That's what I'm trying to do. So this will be the enthalpy of reactants, and since we know everything, we can just go ahead and quickly calculate. In moles of HMX is 1. Enthalpy of formation of HMX, I think I gave it in the question itself. Heats of formation, chemical formula for HMX is 74 kilojoules per mole. Please note that it is in kilojoules per mole, which means we should multiply with number of moles, which is what we did. Okay, and heat of formation of binder is minus 64. Okay, plus 74 minus 64. So this is going to be plus 74 plus Cp of HMX. Ideally, we no need to know. The reason is the initial temperature is also 298 Kelvin. Okay, 298 Kelvin. And number of moles of HTPB is 0.191 into minus 67, I guess, is it 64, okay, 74 and 64 minus 64 plus Cp of HTPB into T initial, which is 298 minus 298. So this part actually drops out, okay, and then this will give you the enthalpy of reactants, which will be in kilojoules. So let's say if I calculate that, 74 plus into 0.0191 plus 74. So I'm getting something like 72.776 7776 or 778 kilojoules. Okay, this is the enthalpy of reactants. Now similarly, we need to find enthalpy of products. That's it. So enthalpy of products, what we have is we have how many products we have? We have CEO, we have CO, H2O, N2 and C. We have 4 products. So we just need to write it down for 4 times. So N of CO into H of formation of CO plus let's consider Cp to be constant again, Cp of CO into T adiabatic minus 298, okay, plus N of H2O, HF of H2O plus Cp of H2O into T adiabatic minus 298 plus N of C, HF of C plus Cp of C, these are carbon, into T adiabatic minus 298 plus N of N2, HF of N2 and Cp of N2 into T adiabatic minus 298. Okay, from the definition we know that H of N2 is going to be 0, This is 0 because N2 is naturally occurring element at 298 Kelvin, and also it's a element, it's not a molecule, so it's N2 is actually 0. And uh, other things, carbon also appears as a, so let's see what they have given. So okay, carbon is also given, so I think enthalpy of formation of CO2 is given, CO is given, and H2O is given. Okay, so we will just so CO2, we do not have CO2, we have CO and we have H2O. For carbon, it's naturally can occur as a carbon, it can occur, right, at 298 Kelvin, so that formation enthalpy also you can make it 0. So if that is the case, this also is equal to 0. Now we just need to put the values. N of CO, how much is N of CO? Let me just copy paste this. So 5.1541 into HF of CO, which is something they are given, plus CP of CO. Let's see. HF of CO is minus 112 and CP of CO is 37. So all are in per mole basis, so we can directly use it. Minus 117, I think it's 32 something, into T adiabatic minus 298 plus number of moles of H2O is 2.8841 into H2O formation is 237, okay, 286.58 minus 286 and 58 minus 286 and 58. So T adiabatic minus 298 Kelvin. I think this was flipped. So 11237. And then you have number of carbon atoms, which is 2.6659 into, you have CP or CP into T adiabatic minus 298, and then you have nitrogen atoms, which is 4 into some CP into T adiabatic minus 298. So I expect nitrogen also should be around like 30s. Usually biomolecules are like 30s, yeah, 37. This is 10.86. So this is 37, this is 10.86. Alright. So now let's if you just add this up, we'll just keep T adiabatic minus T98 as such, and then if you try to add it up, so 5.1541 to 112. If you guys get an adiabatic flame temperature, let me know. This is going to be minus 557.26 plus 286 into 2.8841 so minus 824.85, and then that's it. This is the formation plus 37 into 5.1541 plus 2.8841 into 58 plus 2.6659 into 10.86 plus 4 into 37. So this is coming out to be something like 534.93 into T adiabatic minus 298. Okay, so this is can be written as 557.26 plus 824.85. This is nothing but minus 1382.11 plus 534.93 into T adiabatic minus 298. Alright, so this is going to be your H of products, and we should just equate it, nothing else. So the reactants we already found, it is around one more thing, these are in kilojoules, these are in joules, so you should know that. I hope I did right. So all the formation enthalpies are given in kilojoules and all the CPs are in joules. Okay, so I should be a little careful with that. Oh, where did it go? Okay, so basically into 10 power 3. Okay, all right, so this is going to be equal to 75. So H reactant equal to H product. So H reactant is nothing but 72.778. 72.778 into 10 power 3 is equal to minus 1382.11 into 10 power 3 plus 534.93 into T adiabatic minus 298. So the T adiabatic would be, how much is this coming out? This plus 72.778 into 1000 divided by 534.93. So T adiabatic minus 298 is coming out to be 2719.75 kelvins. So which means T adiabatic would be plus 298.
3017 Kelvin.
Okay, thank you Shantanu. 3017 Kelvin. So this is your T adiabatic. So now what you can do is you can do the same thing. You can do you can find the heat of reaction, okay, and then you can find the and then you can try to follow the steps which we did in the lectures, right? Professor did whatever professor did. If you try to do that, you will again end up with 3017 Kelvin because the concept is actually same. Only thing is the way you do it is different. The way you do it was whatever I explained it here. So what you do is you first find out this thing directly, you first find out this Q directly, and then you are trying to find out the adiabatic flame temperature. What I am doing is I am doing it reverse. First I am directly, since I no need to go from 1 to 3, right? When I have in between steps, so I directly found with 1 and 2, I can directly found the adiabatic flame temperature. So basically at the end of the day, it's first law of thermodynamics, it's H reactants equal to H products. If you do that, it is done. That is how you get adiabatic flame temperature. That is how it is also called adiabatic flame temperature, because the process is adiabatic.
So you're a professor in IIT or a student, PhD student?
I'm actually a PhD student. I'm working. Actually, I'm a PhD student from IIT Gandhinagar. Actually,
Okay.
so my research is actually rocket propulsion. So this is my research.
Okay. Fine.
All right. So this is how you find the adiabatic flame temperature. So adiabatic flame temperature is nothing but temperature of the product species. So that we know. Now we can find the characteristic velocity. So that is straightforward. You guys know what to do with characteristic velocity. So we have a C star formula, right? C star is nothing but What is that formula? Some PCAT by m dot, where m dot is how will you write this? Some gamma times what was the formula? I mean, you guys know the formula. Let me just quickly take a look at it.
So we can simply write square root of RTC divided by gamma. Square root of RTC divided by gamma.
Right. Square root of
RTC.
RTC or RU by molecular weight divided by gamma. Right.
The whole thing divided by gamma.
Gamma.
So gamma is a function of small gamma, the ratio specifically.
Right. So gamma you need to find out. Gamma of mixture you need to find out. This product mixture you need to find out. And after that only you will be able to find the what do you call the C star. So how will you find gamma of mixture? So now
That is a very tricky thing. You know, there has to be a ratio of specific heats at constant pressure and constant volume.
true.
Now, if this specific heat and constant volume is not given in the data, trying to solve the problems, then you are going to go to the net to find out what those
So this is Cp minus Cv is nothing but Ru. Right?
Okay.
So these are all molar basis. When I put a bar, it's molar basis. These are on mole basis. So if you know Cp, Ru is universal gas constant. Cv is nothing but Cp minus Ru.
No, the problem I faced, particularly finding out the values of Cp and Cv, different sources are giving different values. I went on internet and searched different websites. I'm not getting the same value.
So that is
And those values are different from what are mentioned in the assignment.
okay. So the reason could be due to Cp is a function of temperature and Cv is also a function of temperature. The value you use should be a good estimate to get a right temperature. So for example, you have here. So as I showed here, you have Cp as a function of temperature, right? So from 298 to T adiabatic flame temperature. So from initial temperature to adiabatic flame temperature, it's like 2000 Kelvin difference or 2500 Kelvin difference. So in this 2500 Kelvin difference, the Cp also changes. Now the question is, which Cp will you take in between this, right? You can either take, since it's a variation of 2000 Kelvin, let me take like 1500 Kelvin as a, so Cp at 1500 Kelvin is the representative Cp which you are taking. So you can either take that, okay? So it depends upon Cp and also the temperature. So whatever the problem we give, whatever the Cp we give in our problems, it may not exactly coincide with whatever you see in your internet. The reason is, whatever we give is a better estimate of Cp because the temperatures are varying.
That is why it's said as, it's stated as the mean Cp value.
Exactly, true.
But Cv is not given the at constant volume. So how can we find the ratio?
Right.
Both are not given in the assignment.
So if Cv is given, if Cp is given, you can find Cv to be Cp minus Ru.
Okay.
So since we know Cp, since we also know Ru is not going to change, it's universal gas constant, you can find Cp. So if Cp is given, you can
when a rocket is fired, lot of hazardous gases are produced. Tons of hazardous gases are produced all over the world when the rockets are fired in all over the world, different countries.
Right.
So it spoils the environment, right, sir?
Right.
So in this, we got any research going on to find the alternate, or because in the same way like automobiles were finding battery power, Okay. So
Right, I
how
understood.
how to save our environment?
Right. So I'll come
And
to that question.
not only on the ground,
Mhm.
when the rocket is fired, the propellants exhausted, but in the space also, hundreds of satellites, where it uses the thrusters for correction of attitudes and other thing.
Right.
So how to is there any research going on to eliminate to save the environment?
Right. Yeah, I will answer that question. Before that, I want to make sure that uh, Ram sir understood the concept. So,
Yeah,
is it clear? CV is clear?
it's clear. It's clear.
Okay. So, once you know CV and CP, you can find the gamma of each and everything, and or you can find CP of mixture and CV of mixture. Once you find CP and CV of mixture, you can find the gamma of mixture. Okay, you can actually
How do
find
you
the CP
find
of mixture.
CPO mixture? There are two chemicals, two items. So it has to be
Mole fraction
CP,
weighted.
mole fraction weightage has to be.
Right. So if it is a molar basis CP, if it's in joules per mole Kelvin, then you just multiply with the number of moles, add it, and then divide it by total number of moles.
Got it. Clear.
So once you know CP, CV of mixture you can write it as CP minus RU, CP of mixture minus RU, and once you know, you can find the gamma of mixture. Once you know gamma of mixture, this will be known. Molecular weight of a mixture is also molecular number of moles weighted. That is also
Oh,
weighted.
yes.
We just found that adiabatic flame temperature. Then you will be able to directly find the characteristic velocity. So is does that answer your question, Ram?
Yeah, it is clear. It's clear.
Okay. Thank you. So
Thank you.
yeah, coming back to Pala Maitri's question, I will
Yeah,
quickly
this is
answer.
Palasrina. This is Palasrina. I don't have that Google email, so that my daughter
Okay,
Google
no
mail.
problem. No problem. So I will come to that question. So before that, I will formally finish the session so that others no need to wait. So basically, we found the characteristic velocity also. We found temperature also. Heat release we already did it in the last class. But also I would encourage you to do in this way. So let's say as Shantanu was mentioning, you can do a energy balance between these two, which is Q is equal to nothing but the CP of uh, products from T adiabatic to T initial. Okay, like Shantanu said, you can do that and you will end up getting the Q. Okay, so that is also a way to find the heat release. So I hope this should give you a good clarity about the concept and also to solve the assignment problems. If there are any questions, please stay back and ask. If not, we will meet next week. Okay.
So I have a doubt in assignment 5 question 8 actually.
Okay. What is the doubt?
So it's also regarding calculation of the heat of formation or heat of combustion actually. Sorry. Heat of combustion, heat of formations are given of all those chemicals,
Mm-hmm.
and I think it's the combustion of acetylene, ethine.
Okay.
And
Is the answers out? Or
yeah, I'm having a doubt with the answer and even the solution which has now been uploaded.
okay.
Because they have not considered that formation of heat of formation of the reactant in it, I guess. Only the some of the products has been added and the answer is given. The heat of formation of the reactant is not included in the solution.
Which
So that
question
is
is?
the answer is 2711. No? 2711.
Yeah, you can have. I guess you will have.
It is considered heat of reactant is considered, heat of products also considered. It's both. I have solved this problem.
Which question is that?
The solution part Question 8, sir. Question 8.
Okay.
If you can just show me once.
The energy liberated from the stoichiometric combustion of acetylene gas with 25 degrees Celsius with oxygen gas at 25 degrees Celsius, chemical reaction of which is given below. The standard heat of formation is this. Calculate the energy liberated. So basically you need to calculate the amount of heat of reaction, right? Isn't it? That's
Yes,
what
sir.
it means. So what was the problem? Let me look at the solution file. So
Can I, sir? Can I?
No, sure, please.
See, for heat of formation in kilojoules per mole, given for C2H2 is 227, and for O2 is 0, CO2 is minus 393.5, H2O is minus 241.8, and we have to balance the equation. When I balance the equation, it comes to 2C2H2 plus 5O2 is equal to 4CO2 plus 2H2O. And when I take the heat of formation, 2 moles of C2H2, that is into 227 kilojoules, minus of that is the fuel product. Okay, that is the fuel, and reactant is O2 is, however, it is 0. So now 2 into 227 plus 0 is products. That is fuel. Minus of then 4 moles of CO2, that is minus 4 into minus 383.5. Then minus 2 into minus 241.8, that is H2O.
Right.
So that gives the value 454 plus 1574 plus 483, which gives you 2511.6 kilojoules.
Yeah, actually the solution file they have given is actually wrong. They didn't add the 2 times C2H2 here. If you look at it.
Okay.
So whatever Pala said was right. So if I just calculate this is coming out to be just 2057. So if you add the 2 times 250, you will get 2511.
Yeah. Okay.
So the solution file, I think it's wrong, but the solution is right. Were you able to get Akhileshwar what he was telling?
I'm trying once again.
So see, look at this. Its enthalpy of reaction is nothing but, so this 227 is not been added in the solution file, but ideally you should add it. Understand? So it is something like this. Enthalpy of Q of reaction or energy liberated is nothing but 2 times this 227 minus 4 times CO2. CO2 is 393.5 and H2O is 241. 393.5.
Minus 393.5.
Right. And 2 times 241.8 something. 241.8 minus that is also. Okay. So when you do this calculation, you will end up having 2511. Okay.
Yeah.
So 2511 kilojoules. So if you do this calculation, this is products part. The products part they didn't add it in the solution file, but I think it's a typo error. So while they write it, they missed that part. So this is how you should. This is how you should actually get the heat of reaction. Okay. Any other questions? Any other question anyone else have? Or if not, I will directly address the question of previous question of.
Yeah.
Okay. So
Can I say? What any fuel research of fuel where it doesn't harm the environment.
Right. So actually there are a number of fuels. So for example, the main problem is the chlorine content of this fuels. So what happens is they release chlorine containing compounds. So usually in solid, I think you since you are also studying about solid propellants. So in solid propellants, what we have is ammonium perchlorate and HTPB propellant, right? So this has chlorine containing compounds. So this is the main problem. Problem causing products coming from the propellant. So only thing is because of this, the alternative is something like ammonium nitrate. They are trying ammonium nitrate, HTPB propellants for the solid propellant type, and these are all for solid. But in liquid, this is not the case. For example, you can simply use liquid hydrogen and liquid oxygen. So that is not
non-polluting. Yeah, this is non-polluting.
This is not a pollutant. So at the end of the day, you are going to get H2O. That's it. So this is not a pollutant. For liquid, that's why in cryogenic engine or liquid propellant engines, there is no problem. Only thing is the solid propellant engines and the solid propellant rockets. Solid propellant rockets are the one which we use it for takeoff. And we don't use solid propellant rockets in anywhere else. We don't use it for higher stages of rocket. We don't use it for satellite attitude correction, or the orbit correction maneuvers. All those things we don't use solid propellant, simply because you cannot control it. It's once you ignite it, it's just going to just completely consume the propellant, and then only it stops. Liquid propellant is not the case.
They are cold gas. In satellite attitudes, that is cold gas rockets.
Right, cold gas rockets they use. Even they use actually hydrazines. Hydrazines are they use hydrazines. MMS. This is like this is very difficult to handle because it's so reactive. It can easily cause explosives. So it has only safety concern. It doesn't have like eco-friendly concerns. It has safety concerns. But this is what they use in maneuver correction because it's more efficient and highly reactive. And also it can the monopropellant also people use. For example, people use something like nitromethane, CH3, I think NO2, nitromethane. The reason to use this as a propellant is it has both fuel and oxygen in it. So like we saw in HMX, so which has fuel and oxygen within itself. You don't need to have additional tank. You don't need to carry additional tank. You don't need to carry additional pumps to send fuel and oxidizer together and combust. It's just one nitromethane tank you will have. You will just send it into the combustion chamber, ignite it, and it's first CH3 NO2 becomes CH3 and NO2, and NO2 acts as oxidizer, CH3 acts as a fuel, and they combust and they react. So that is people are exploring. It's a efficient efficient monopropellant rocket. So that is these things they use it for satellite. It's for minute orbit correction, satellite attitude correction places they use it. For only in the first stages of rocket, because you need enough thrust to carry like thousands of tons of load. You need to lift the 1,000 tons of load together. You need a more powerful rocket which has high mass flow rate, and solid propellant actually provides that mass flow rate, very high mass flow rate, high velocities. So you will get high thrust in order to lift your rocket from the ground. That's why you see solid rocket motors and boosters you will see only in the first two stages, and that is only its main eco-friendly concern because they use APHTPB and it has chlorine containing compounds. And alternative is they can also, the research is going on, they can also use ammonium nitrate and HTPB. The other alternative is they use simply aluminum and water.
Okay.
This is the propellant actually, aluminum and water. It gives you aluminum oxide plus hydrogen gas. So, but this is not that much efficient. Actually, I am doing research in this propellant actually, aluminum and actually it's metal based propellant. We call it metal based propellant. It has aluminum particles and it has water vapor, and these two reacts and gives us Al2O3 and H2O. Even though it promises higher theoretical it actually promises, for example, if I try to find the ISP of this, it is around like two I think it was around like 246 seconds. So the ISP of AP-HTPB propellant, AP-HTPB propellant, okay, this is around 270 seconds, 270, 269, around that seconds. So this is comparable. I mean, it is not that much. It's a huge difference in terms of ISP. It's like getting an improvement of 10 seconds itself is a very big deal in terms of ISP. There is another people are exploring. It's nothing but aluminum hydride, or aluminum with hydrogen peroxide. Hydrogen peroxide is very highly chemically reactive. So this also people are working, and its ISP is very high, even higher than the HTPB. It's around like 320 seconds, 320 to 330 seconds, which is higher than AP-HTPB. But people not using it because you are not able to get this 320 seconds, and that's why active research is going on this, so that if we are able to get this 320 seconds ISP, experimentally, theoretically it says 320 seconds, but experimentally if you are able to get this, then we can directly use this. And these propellants doesn't have any it is eco-friendly in nature. Its exhaust is very exhaust doesn't contain any chlorine containing components, and you got only what you call hydrogen, which is just benign gas. And similarly, water vapor additionally you will get. That is the only thing you will get. The additional advantages you will get from here is the aluminum and water are actually found in other planets. Let's say if you are going for interplanetary exploration mission, you can use the metals present in the moon. So you no need to carry both fuel and the propellant. You can carry you no need to carry both fuel and oxidizer. You can carry either one of them. For example, aluminum is abundantly available in the entire solar system. So you can go to Mars or you can go to moon. You can take the aluminum, but only thing is you need to you need to do a reduction mechanism to what aluminum we get will be in terms of ore. You need to convert it into aluminum particles, and once you convert into aluminum particles, it is your fuel. So you can go to moon, you can make your own fuel, you can use water, you can take your water with you, water or hydrogen peroxide with you. So you don't need to carry whole fuel, you need to carry only component of a fuel. This is going to save you much. So that is, we call it in situ propellants. That is also, there is active research going on this in situ propellants. Basically, currently this is the alternative we have in terms of eco-friendly nature, but this is in highly research stage. It is not at all in implementation stage, because there if I look at it, the actual ISP I get, if I do the experiment, the actual ISP I get is around like 140 150 seconds, and we still don't know why it is happening. And only if we find out what is the reason for this, we'll be able to improve it, we'll be able to use it.
Sir, most of aerospace is that proven track record. That's all.
Right.
Since the other propellants have proven well while propelling the rockets.
Exactly. So people will not remove. We cannot go out of it. Ammonium perchlorate, APH.
They cannot.
They cannot do, because it proved its thing.
Yeah, one more discussion. What I want to initiate is there is a comet which is going to hit the Earth. Somewhere there is a news. Now, as per the universal law of gravitation, between suppose you make one satellite to deflect that, to deflect the path of the comet, because comets doesn't have the path. So you can only deviate it from the Earth orbit. So for that, my question is whether I have to design or have a satellite which is heavier than comet, and if it is so, how I can take it to that height? Such a heavy comet, such a heavy satellite or truck or something like that.
So,
Or there is also talk that by a small satellite also it can deviate the orbit or the path of the comet. But as per law of gravitation, the smaller mass objects are attracted towards the heavier objects. So in this regard, I just want a little clarification.
So there are different ways of deflecting, the asteroid or something. One thing is we will send a rocket, we will try to destroy it, we will try to break into pieces, you will try to get it out of the orbit. The other thing is, I think you are mentioning, is using a gravity pull. So
Yeah.
you will take it to some place where you can basically uh, exert some gravitational pull on the asteroid so that it gets deflected from the Earth's orbit. So is that what you are?
Yeah. Yeah. One is blasting it. Blasting it is easy, but what are the other influences of that blasting? We don't know. Second is this deflecting is a more tricky one. But the clarification is that whether with a small satellite I can deflect by creating a small gravitational force between them, or if I create a lighter weight satellite or whatever it is, whether that will again get attracted towards the asteroid or comet. This I need some clarification, sir. Because if I have a heavier satellite or anything, then that will definitely attract the comet because of the universal law of gravitation. So its path will get deflected.
Correct.
Or I have to take many satellites clustered together and hit that or deflect that. So I don't know about the technique we use generally. Who is also taking up this task, whether NASA or India or who, that also I am not sure. But at least for knowledge sake, I just want to know that.
Actually, it's in the active research area. Even I'm not very sure about what are the techniques they have for this kind of thing. It's all too complex to deflect an asteroid. First of all, detecting an asteroid itself is a very difficult process. That was one of the challenges we have, finding the asteroid, whether it is coming or hitting or not. So to get that itself is a difficult process. In addition, if we come to know, I don't know what are the strategies in place to do it. Recently, what happened? There is this NASA mission. I think it's DART. You might have known about this. It's called Double Asteroid Deflection. Some DART actually. DART mission.
Okay.
What they tried to do is they tried to send a satellite, and they tried to crash on that satellite. So basically, they tried to send a satellite to an asteroid. It's a double asteroid actually. Two asteroids, rotating together, and then it's revolving around. So what they tried to do is they tried to go and hit a smaller asteroid, something like that. They crashed on it, which exerted some force, and because of that force, the bigger asteroid also got a little bit deflection, and because of that, their orbit got changed. So that they were able to do. And actually predicting this, it's not so easy from the it's a universal law of gravitation. In the universal law of gravitation, till now what we have studied is we just took a two body, and then we tried to see when it is revolves around what is the velocity, orbital, everything we try to do. But in terms of asteroids, it's no more a two body, it's like a n body problem. You will have so you will have a gravity experience. Asteroid will experience gravity from not only just Earth or Moon, it also experience gravity from other asteroids too. Because asteroids are small, other asteroids will be big. So with these two, it has experiences gravity, and based on this, the orbit will be changing in a chaotic way. So let's say by any chance, if we, let's say, crash it and then try to deflect it, we will not know for sure whether that deflected orbit will actually make the things worse or make the things better. For example,
Again, it may come after some time also.
it can come after some time, and we also do not have, since it's a n body problem, it goes into the chaos theory and all the nonlinear fancy stuff, mathematics. So it is very difficult to predict what would be the orbit of asteroid. So even if we come up with the strategy, upon performing that mission, we will not be for sure telling that this is what will happen for that asteroid, simply because this dynamics is very complicated. It's very complex, and we cannot solve it with any computers too.
And the moon is a satellite to Earth. Moon is saving from many asteroids, right? Many asteroids are hitting moon. Because of that, you are finding the craters when you see the moon surface.
It could be.
Yeah.
I'm not very sure about it. Yeah, it could be. It could be, because it also gives some gravitational, gravitational pull. Exactly. So because of that, because of that, it can do that. True, you're right. But I'm not very sure about this.
And
These all goes into
Jupiter,
astrodynamics concepts.
Jupiter is attracting lot of comets. Lot of comets are hitting Jupiter. The reason is gravity at Jupiter is more.
Yeah, so actually what happens is it the whatever we revolve around, we don't revolve around sun, we revolve around at a certain point, which is actually which is not at the center of the sun. The reason is because of Jupiter. So Jupiter's gravity is too high. It actually even sun rotates around this center because of this Jupiter's gravity.
Okay.
That is
can we use the same concept for to deflect this, having a more gravity satellite?
but building a more gravity satellite is also a challenging problem, right? How 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 big your mass should be? It cannot be like the mass of the moon. That is simply impossible to do it. Mass of the if we make satellite to be equivalent to mass of moon, then it is becoming, we just don't have resources to make it. It depends upon which which asteroid we are trying to deflect, and also it depends upon how big our gravity should be. Yeah.
Okay. No, just we can have a brainstorming whether any physical principle we can use to increase the gravity with a smaller satellite. Like a huge magnet, we can say something like that.
Increasing gravity, I haven't came across such physical concept. Yeah, it
No, because the comet weight may be in tons, so sending a satellite heavier than that is ruled out. That is very difficult.
yeah,
The only option is to blast out the comet.
exactly.
That is one option. But blasting what influences other influences it gives, we don't know.
Correct.
That is number one.
Right.
So anyway, the best way is deflecting it. So deflecting, like how comets are deflected towards Jupiter. In the same way, without heavier mass, whether we can increase the gravity, some physics we have to. We may also put a thought on that.
Yeah.
Yeah. Okay, sir. Nice meeting you.
Actually, you all no need to call me, sir. You can just directly call me Ganesh. It's call, and it's for everyone. I'm not yet a professor, so.
Yeah. Thank you, Ganesh. And you are working anywhere or only PhD student?
Yeah, I'm a PhD student. I'm a full-time PhD student.
Okay.
All right.
Right,
Thank you.
sir.
Thank you. Thank you, Akhileshwar.
Thank you.
Thank
Very
you,
well, sir.
Ganesh sir.
Thank you very much, sir. Nice talking.
Thank you.
Thank you. Bye bye, sir.
Bye.
Thank you, everyone.